All right, 9.4 talks about these terms electrolyte and non-electrolyte. Okay, um, the way these terms came from whether or not electricity travels through a solution. Okay, both these compounds dissolve in water. So electrolytes, they dissolve in water, and non-electrolytes, they also dissolve in water. And you've probably heard these terms when you talk about a sports drink or some sort. You replenish your electrolytes, right? Electrolytes, when they dissolve, they conduct electricity. These are ionic compounds. Okay, non-electrolytes, they dissolve in water, but they do not conduct electricity. These are mostly molecular compounds. All right, and if you remember, a molecular compound is where you have all nonmetals, like sugar, for example, C6H12O6. If I take sugar and dissolve it in water, it dissolves, but it doesn't ionize. I don't have ions. You have to have ions. This is kind of showing you how an ionic solid right here, it ionizes in water, breaks apart into its individual ions. Here's the chlorine ions with water around it, the partial positive ends, so the hydrogen ends, are attracted towards the minus charge of the ion, and your positive end, your negatively charged oxygens, are attracted towards the ions. All right, because remember, your oxygen's more electronegative, so that's partial negative, your hydrogen's partial positive. That was from last exam. Okay, so because you have these charges, electricity can actually travel through these, and you call it an electrolyte. Sugar does not have ions, so you have a non-electrolyte. And you can actually see this. If you just have pure water, nothing dissolved in your water, just pure water, electricity will not travel through it. All right, you have to have ions in order to have electricity travel through it. So here's a great example. This is kind of a setup. You can actually go on YouTube and do something like electrolytes light bulb. You'll find a video, tons of them, that kind of show you this experiment. What it basically is, it's a light bulb that's attached, it's attached either to a battery or it's plugged in, and you have these two leads here. You can't really see them, but you have one lead here, all right, and you have another lead right here, okay? And in this case, you have pure water. Notice the light bulb is not shining because the electricity can't travel through pure water. Okay, in this solution down here, you've got ions floating around. Well, the electricity is able to travel from one lead to another lead, and you now have a closed circuit. So the light bulb is shining. In this case, this looks like glucose. If you have a glucose solution, which is a non-electrolyte, and put the light bulb in, electricity can't travel through glucose, so the light bulb is off. Okay, so technically, if you were taking a bath in a bathtub of just pure water with no ions in it, and you threw in your hair dryer that was plugged in, you would not get electrocuted. You'd be totally fine. Granted, I would not try this experiment because it's pretty hard to get just pure water, especially your body is filled with ions. So as soon as your body goes inside the water, all the ions are in the solution. So please, as a disclaimer, do not try this at home. But in theory, if you were in water with no ions at all and threw in a hairdryer, you would be totally safe. Okay. Um, levels of ion dissociation. This is depending on the type of ions you have. So notice you have a barium nitrate. Barium has a 2+ charge, nitrate has a 1- charge. So the formula is BaNO3 2. Okay, so that means when you take this and you dissolve it in water, you'll always have twice the amount of nitrates compared to your barium. Okay, so notice you have 4 barium ions, but you should have 8, 1, 2, 3, 4, 5, 6, 7, 8 nitrate ions. All right, here it's a 3 to 1. 3 chlorides for every 1 aluminum. Okay, so you have 2 aluminums, therefore you should have 6 chlorines. Okay, and then sodium phosphate, you should have 3 sodiums for 1 phosphate. Okay, so that's how they're talking. What are they talking about? Like the levels of dissociation. Okay, so here's a concentration problem. Okay, this is a very interesting problem. All right, it takes what you learned from molarity, and then it takes what we just learned in the previous slide. Okay, it's actually using like mole to mole conversions in a way. Okay, so determine the concentration of the chloride ions. Okay, let's do, I guess, let's do A. If I have a 0.1 molar solution of lithium chloride, for every one lithium chloride, there is 1 mole of chloride ions. So if the molarity of this is 0.150, the molarity of this is 0.150. Okay? Now, in the magnesium chloride, for every 1 magnesium chloride, I've got 2 chloride ions. Well, if I take a 0.15 molar solution of this, I'm going to have twice the amount of that. Okay? And then for the aluminum chloride, I'm going to have 3 times the amount. Okay? So it's that straightforward. All right? So again, this is a mole to mole conversion. See that? We learned that last exam. However many moles of that ion, that's the concentration of it. Okay? So I'm going to have 3 times the concentration of chlorine with respect to aluminum based on the molarity. Okay, so again, this shouldn't be anything hard. It's something we learn, and it makes sense. However many more ions I have, you just compare from your molecule compared to the individual ions. Okay, this is kind of the 4 different ways that you can prepare a solution. You can do it by weight, you can do it by mass. There's a whole bunch of ways. You're going to have a problem set which kind of incorporates all this, so I'm really not going to go over this list. You can obviously read the list, but this is kind of just all talking about how you do it. All right, but these problems kind of are good to actually go through. I'm not going to go through them right now because we've kind of gone through these, but it's basically saying, how do you prepare a solution? Okay, so for an aqueous solution of glucose, determine the molarity of 2 liters of a solution that contains 50 grams. This is kind of a summary of everything. Okay, so the molarity, you have 50 grams for 2 liters. Okay, well, you convert this to moles and then take your moles and divide it by liters. That's your molarity. Okay, so you can do these on your own. We've kind of done these types of problems already. It should be pretty straightforward. Okay, the next one I want to talk about, though, is when you want to go from a more concentrated solution and you want to dilute it down. Okay, so imagine I have a stock solution of, let's say, 6 molar hydrochloric acid, and let's say I want, let's say, 50 milliliters of a 1.0 molar solution. Okay, so let's say I have a gigantic bottle of this in the stock room. I obviously don't need all of it. I only need 50 milliliters, and I need it at 1 molar. I don't even need it at 6 molar. So how do I do this? I have to take out a small amount of this, okay, and put it into a smaller container, all right, and make a total of 50 milliliters. So I got to figure out how much of this I need and how much water I need in order to make my 50 milliliters of 1 molar solution. So that equation is right here. Now, they use C's for concentrate and dilute. The way I was taught, and a lot of other people have heard it, is M1V1 equals M2V2. Same thing. M is your molarity, V is your volume. Okay, so I'm starting out at 6 molar, and I don't know the volume of this. That's what I'm trying to find. Okay, I'm going to call it as V. My new molarity is 1.0, and my new volume is 50 mils, but you have to convert it to liters. So this is my equation. So you solve for V. V is 1 times 0.05 divided by 6. Okay, so let me do that real quick. So 0.05 divided by 6, and you get, this is in milliliters. I'm going to convert it, I'm sorry, this is in liters, 0.0083 liters. I'm going to convert it back to milliliters, which is 8.3 milliliters. Okay, so what does this mean? That means I need to take 8.3 milliliters, so 8.3 milliliters of my HCl of the 6 molar. So this is 8.3 milliliters. And then how much water do I need to add in order to get 50 milliliters? Well, if 8.3 of it is the HCl, right, I just take 50 and subtract it. So 41 point, oh, man, I hate when that happens. Where are we? 41.7 milliliters. 41.7 milliliters of water. So how do you make a 1 molar solution, a 50 mil 1 molar solution of HCl starting with 6 molar HCl? You take 8.3 milliliters of HCl and dissolve it or add 41.7 milliliters of water. Okay? So that's how you do these molarity problems. Here's a bunch of them. You can kind of work on this same exact problem. Look, you're starting with 12 molar this time, and you want to make 250 mils of a 0.125 molar solution. All right? So you can do that on your own. All right? So, like I said, I'm going to post practice problems for you, and you can work on those. All right? And we will stop the video right here.